Swayam Prabha. Digital India. Educated India.
Okay, so I have uploaded a problem sheet in Moodle. It will have part 1, part 2. Part 1s are questions that I will solve in this class, and part 2 are some extension. It's for you to practice, and you will see the questions are very similar in kind, but it is basically an exercise for you to do. So the problems in the problem sheets are actually curated such a way that it actually aids our understanding of the concepts we discussed, okay, while doing problem solving. So this is a particular question asked in GATE 2020, okay, not long ago. It basically asks about the resistance for mass transfer in liquid phase versus its overall resistance, okay. So here maybe it's good to kind of highlight the important things. So we are talking about absorption of a solute from a gas mixture into a liquid solvent. So it's basically an absorption problem or diffusion of A in a non-diffusing B type problems. And then they have given the mass transfer coefficient values. You can note the units for the gas side as well as for the liquid side. And then the equilibrium relationship is also given in terms of mole fractions. And the question is, what is the ratio of the mass transfer resistance in the liquid film or liquid phase over the total resistance, okay. So first of all, to answer this question, it's a good practice to list out all the known data, okay. So what are the known data? First of all, I want to write that it is a diffusion of A in non-diffusing B. Type mass transfer, okay. So type of mass transfer, we will note it down. Then we are given with the local mass transfer coefficients. Kx is 3 mole per meter square per second, and Ky is 0.1 mole per meter square second. Now in this particular equation, so they have deliberately not used any symbols for the mass transfer coefficients, and we already said that the mass transfer coefficient symbols are quite confusing depending upon the type of the mass transfer, which phase, which concentration units used. So there are a lot of possibilities. So to avoid the confusion, here they have not mentioned any symbol. However, I have written small kx, small ky, okay, because I already know what's the diffusion type based on the problem. So these are all quantities without prime, okay. Primes are used for equimolar counter diffusion, so that is one. Second is, I looked at the units of the mass transfer coefficient. It's given in the flux units, mole per meter square per second. It also means that the concentration units are in mole fraction, even though mole fractions are also given there, but still you have to look at infer the mole fraction units from the mass transfer coefficient also. So then if I have a liquid phase with mole fraction as the concentration unit for A diffusing, non-diffusing B, I have been using in the last few classes this notation small kx, x referring to liquid phase mole fractions. Similarly, I am using for the gas phase small ky, because y is the mole fraction in the gas phase and the units are also same, okay. So here I infer based on the type of the mass transfer type as well as the concentration units and the mass transfer coefficient units, what symbol I should be using, okay. So this is given, and what we are also given is the equilibrium line. So that is y star is equal to 2 times x. So this is also given to us. So now to understand the mass transfer resistance in the liquid side versus the overall resistance, first we will calculate the overall mass transfer coefficient, which I call KL, capital KL. Okay, this is something, if you go back to your notes, you will see we have defined this as 1 over Kx plus 1 over M Ky. Here we have used M prime, M double prime, but that's only cases where the equilibrium line is curved with the different slopes. This problem is much more simpler with equal slope across the range of concentration. So M prime, M double prime are actually equal. So I'm going to use just M, and the value of M is 2. Kx is known, M is known, Ky is also known. Okay, so we can just substitute and then get KL. Okay, now the question asked here is, what is the ratio of mass transfer resistance in the liquid film to the overall resistance? So this is basically the overall resistance. And this is the liquid phase resistance. We just need the ratio of the two. Okay. So I'll simply say ratio. We know what this ratio means. So first I have the liquid phase resistance, which is 1 over Kx divided by 1 over KL. This is the quantities of interest. So in other words, it basically becomes KL by small kx. Okay. Kx is already known. It is 3. KL we don't know yet, but we can obtain from here the value of KL. So which is nothing but, so we'll first get 1 by KL. So 1 by KL is equal to 1 by 3 plus 1 by 2 times 0.1. So from here, if you calculate KL, you will get 3 by 16. And then if you substitute that KL here, you will get 1 by 16. That's the answer, which is equal to 0.0625. Okay, and that's basically this particular answer. Is it clear? It's the most simplest problem. Everything is given. It's about substituting and understanding how to define resistance. So here, this problem we have solved using overall liquid phase resistance. Okay, KL. You can do the same problem with KY also. Okay, you could have done this problem by calculating capital KY by defining 1 by KY is equal to 1 by K small y plus M by small kx. You will get exactly the same answer. Okay, so it's either way. The answer suit, you can. It's a very simple problem, so you can choose either of these ways. Okay, so basically the answer is 0.0625, and that's option C. So let's move on to another question. So this is a GATE 2017 question. So it talks about a steady state mass transfer. Steady state mass transfer of a solute A from a gas phase to a liquid phase. Again, more like absorption like problem. It also tells the direction. It's going from gas A to liquid. And they have also given the mole fraction of the species in the gas phase at the bulk as well as at the interface. Same notation that we used in our lecture. YAG, YAI. A referring to the solute, G referring to gas bulk, I referring to interface. Similarly, the liquid phase bulk and interface mole fractions are also given as XAL and XAI. Again, same notations. Now, they have said that the ratio of XAI minus XAL and YAG minus YAI is very close to 0. This is the information given. And they are trying to ask, what about the mass transfer resistance? Where does it lie? Is it negligible in the gas phase, or is it negligible in the liquid phase, or is it negligible in both cases, both phases, or they are both limiting? Okay, these are the choices. Okay, so we have to make this decision based on the information given. In order to do this problem, first of all, you may recollect I was showing this diagram where I have the equilibrium line. This is y versus x. This is the equilibrium line, y equal to some function of x. It's an absorption, gas to liquid. So the initial composition, bulk composition, can be represented somewhere above the line, and then the interface concentration can be somewhere here. Okay, and we already said what is the slope of this line, and that is governed by the mass transfer rates. Okay, the slope of this line is small kx by small ky. Okay, and the equation of this line we have discussed is YAL minus YAI. Sorry, this is not L, this should be G. Okay, so YAG minus YAI divided by XAL minus XAI is equal to minus Kx by Ky. So this is the equation for the driving force line. Okay. This YAG is here, XAL is here, these are the bulk mole fractions, and these are the interfacial concentration, YAI and XAI. Okay. Now, if you look at this particular, what is given? So, given expression is XAI minus XAL over YAG minus YAI. This ratio is close to 0. Okay. So, maybe what we could do, we can actually take this equation of this driving force line and write it in this format and see what it means when this ratio goes to 0 in terms of mass transfer coefficients. So, first of all, we will invert it. So, if I take this, so inverting equation 1, you will get XAL minus XAI over YAG minus YAI. Okay, when I invert it, I get minus Ky by Kx. I just inverted it. And if you compare these two, are they same? No, there is a sign problem, right? So here what is given is XAI minus XAL. What we are looking at here is XAL minus XAI. So we just multiply by minus 1 both sides. So I'm going to get XAI minus XAL over YAG by YAG minus YAI should be equal to Ky by Kx, and this ratio goes to 0, which means Ky goes to 0. Okay, or Kx is very large. Maybe Ky is finite and Kx is very large, or maybe Kx is finite and Ky tends to 0. Okay, so what that means? So then which phase is limiting? The phase which has the smallest mass transfer coefficient will be limiting, right? So which phase is limiting? So Ky is tending to 0, so gas phase is limiting. What is negligible? Liquid phase resistance is negligible. Okay, so we can go back here and then see which one is negligible. Only the liquid phase is negligible. So we take option B. Okay. So this particular problem is a little bit tricky because conceptually it's all simple, but the way they have given the ratio, inverted the ratio, and instead of asking which one is resisting, they are actually saying which one is negligible. So it's very easy to make mistakes by not inverting it. Okay. Generally students will just say this is equal to minus kx by ky, and that tends to 0, meaning liquid phase is very small. So the liquid phase is actually limiting, so gas is negligible. So there is a chance of making a mistake there. Or in the options are giving in terms of resistance negligible, but what we actually calculate is which resistance are actually important. Okay, so there's a little bit of tricking the student in terms of jumbling the words and asking different information given a totally different kind of information. So you have to be a little bit careful about what is being given and what is being asked, and you have to pay attention. So that's the, otherwise conceptually this question is very simple, but it's all about how we understand this particular terminologies and what is being asked and what's being given, and you have to kind of turn it around a little bit, right? So in this problem, so we have air with solute P. Generally we say solute A. So here they have given P, so it can be any letter. Okay, so we are going, instead of A we are going to use P as a index for the solute, otherwise the same thing. It's in contact with water. So again we are talking about something like an absorption like problem, meaning that so in this case not A, we are going to say P diffusing in non-diffusing B. Okay, so P diffusing in non-diffusing B. Okay, so B is the other solute, so that's a type of mass transfer. So we have to note that down, and then it's steady state. Bulk concentration of P in air and water are given. Okay, so what notation we should use? Bulk concentration of P in air. What's the notation? YPG. Yes, very good. YPG. Okay, you should be able to adapt the notation for a given situation like this. So YPG is 0.3, and then the bulk concentration of P in water, what's the notation? XPL is 0.02. Okay, and then we are given with the equilibrium relation for the interface mass transfer. YPI is equal to 0.25 XPI. They have not said this is an equilibrium curve. They have said this is a relationship that is followed in the interface. You may recall I already said the interface do not have any resistance for mass transfer, so the interfacial concentrations are essentially equilibrium concentrations, meaning this interfacial composition relationship is actually the equilibrium relationship. Okay, so we can interpret this as Yp star is equal to 0.25 XP. Okay, so this is another trick to confuse a student by giving the interfacial concentration. So one may be confused about whether the equilibrium concentration, whether this equilibrium curve or is an interfacial concentration relationship. Okay, but basically they are the same. And then in this problem, they have also given the mass transfer coefficients as Fg and Fl are identical. Okay, Fg is equal to Fl. In terms of values, they are the same. And the question being asked is, what is the gas phase mole fraction P at the interface? Okay, which is YPI. What is this? This is what we want to solve. Okay. So this problem, also if you look at this mole fraction is about 0.3 and on 0.3, and it's going to continue to decrease. So whenever the mole fractions are more than 0.1, you have to consider them as a concentrated systems, not as a dilute systems. Okay, I already talked about how to write mass transfer flux in two possibilities. One is using the fundamental laws of mass transfer, another one is the phenomenological approach. The phenomenological approach is only valid when you have a dilute mixtures in the gas phase as well as the liquid phase. How do I know which is dilute? You basically look at the mole fractions, make sure the bulk concentrations are not more than 0.1. We are basically talking about 10%. Anything more than 10%, we have to use the fundamental laws of mass transfer, use the F-type mass transfer coefficients. Okay. Now, in one of the problem before here, I used this particular driving force line equation based on the phenomenological approach. Okay, assuming that it is a dilute system. Okay. Now, in this problem, we cannot use that equation for the driving force line because it is a concentrated system. Okay. So, I am going to write the expression for flux using the fundamental law of mass transfer approach, and then I am going to solve for the interfacial concentration. That's what being asked here. Okay. So, there are two unknown interfacial concentration XPI and YPI, but there is an equilibrium relationship connecting these two. So, I should be able to solve for the YPI. So, first we will write Na. The expression for Na is F times ln of 1 minus YPI by 1 minus YPG should be equal. Okay, so here I am going to put the suffix G referring to it's a gas phase F coefficient, and that must be at steady state equal to ln of 1 minus XPL by 1 minus XPI. So, this is what we are going to use. We are given with the ratios of these values, they are actually equal in this case. YPG, XPL are known, but these two are unknown, but we can use the equilibrium relationship to relate the one and get the other one. Okay. So, clearly FG and FL will cancel, and you can also take the logarithmic term out. So, you will get 1 minus YPI over 1 minus YPG is 0.3. On the right hand side, you have 1 minus XPL, XPL is 0.02 over 1 minus XPI. So, now I can rewrite this XPI using the equilibrium relationship which is here. So, this is going to be YPI divided by 0.25. Yeah. So, now you basically have only one unknown here. Okay. So, from here you can solve for YPI. I will give the answer directly, but you can solve this. You get 0.0663. So, that is basically option A. In a way, if you think about it, this problem is very nicely designed so that even if the student don't use the fundamental laws of mass transfer and directly use a phenomenological approach, the fact that the FG and FL are equal basically makes the two method equal. So, even if the student says FG is actually KY and FL is KX, you will still get the same answer. So, there is a benefit of a confusion given to the student that even if they are not familiar with the F type, they could have just simply consider this as a K type and they would get the same answer. Okay, but we wanted to make sure that we do it right, and given because in many colleges this F type K type concepts are not used much. So directly it is phenomenological approach is given, and they may only know about K type coefficients. Okay, so but suppose if Fg and Fl are not equal, okay, the fact that you have this logarithmic term will get a power exponential, will get a power law for the interfacial concentrations, and you'll get totally different answer. Okay, I'm going to show one example towards the end where the Fg, Fl are not equal, and there is a difference between the two approaches. Okay, so but this case is either way. If you solve this with the phenomenological approach with F and F is as K, you'll still get the same answer. So this is a GATE 2015 question. So consider a steady state mass transfer between well mixed liquid and vapor phases of a binary mixture comprising components A and B. So this is clearly not a diffusing non-diffusing B. It is actually a equimolar counter diffusion because both phases contain A and B. So both are diffusing in both phases. Okay, so the type of mass transfer in this case is equimolar counter diffusion. So this is the type of mass transfer in this problem. The mole fraction of component A in the bulk liquid XA. We use XAL, but they have given XA, so we will say XAL is 0.36, and the bulk vapor, we call this as YAG, is 0.16. The mass transfer coefficients for component A in the liquid and vapor phases are given. So Ky is 0.05 moles per meter square second, and Kx is equal to 0.1 mole per meter square second. Do you want to correct me here in the use of mass transfer coefficients? Am I using the right types? Yes, I should use a prime here because it's a equimolar counter diffusion type, and the units are in the units of flux, so it's in mole fraction units. The concentration should be in the mole fraction units, so this should be fine. The vapor liquid equilibrium can be approximated as Ya star as 2XA, and this is valid only if XA is less than 0.4. Otherwise, it's not linear anymore. Okay, it's maybe linear only part of the for part of the composition. So the question is to calculate the mole fraction of A in the liquid at the interface up to 2 decimal places. So basically, we are asked what is XAI. So since it's the equimolar counter diffusion, here the flux is actually same. It is always written in terms of concentration difference, if whether you use K type or F type. Okay, the form is the same. You have the difference only in the case of A diffusing through non-diffusing B. Okay, as far as it's a equimolar diffusion, you can write the equation for the driving force line and then get the interface concentration. So the equation for driving force line is YAG minus YAI by XAL minus XAI is equal to minus KX by KY with a prime. Okay, so this is equal to minus 2 because it's 0.1 by 0.05, it's 2, minus 2. So what we can do, we know this, we want to calculate this, we don't know this, but we can use equilibrium relationship to replace that. So YAG is 0.16 minus YAI, I'm going to use this relation, which is 2 times XAI over XAL, which is 0.36, minus an XAI, which is unknown. This must be equal to minus 2. Okay. Like I said, in the case of equimolar counter diffusion, the flux is still written the same way as a concentration difference. Okay, it's only the difference comes only in the other type, A diffusing through non-diffusing B. So this is a GATE 2003 question paper. Okay, so basically this is a where is it? Draw pen. Yeah. So experiments were conducted to determine the flux of species A in a stagnant medium across a gas-liquid interface. Okay. The overall mass transfer coefficient based on the liquid side for dilute system for the above was estimated to be this. So okay, so a lot of information. The overall mass transfer coefficient based on the liquid side for dilute system. So what symbol should I use here? K? KL, right? Capital KL, and that is 4 into 10 power minus 3 kg mole. Remember, it's a kilogram mole. Kg mole means kilogram mole over meter square second. Equilibrium data is given, y is equal to 2x. What is being asked is what is the flux Na, and additionally gas phase bulk concentration is given, which is YAG 0.4 and XAL is 0.01. So it is A diffusing in a stagnant medium, so meaning it's A diffusing through non-diffusing B, and then overall coefficient is given, YAG, XAL is all given. So we have to find the, we have to basically write Na is equal to, we are going to use overall coefficient, and what would be the driving force. So recall that I have this equilibrium line and I have, this is YAG and XAL, and this is YAI and XAI, and so now so instead of taking this, we could take this entire concentration gradient and use the gas phase overall coefficient, but that is not given. What is given is liquid phase overall coefficient. So then instead of taking so XAL to XAI, we should be taking the X star, which is in equilibrium with YAG. Okay, so that is this. So XA star minus XAL. Since I don't know XA star, but I can get it from the equilibrium line corresponding to YAG. Okay, so equilibrium line is given here as 2x. So this would be YAL over 2 minus XAL. Now all things are given here. It's a very straightforward problem actually. Maybe I overanalyzed, which happens all the time. Okay, so YAL, actually it's not YAL, it's actually YAG. So it's 0.2 minus 0.01. Okay, so this should give you something like 7.6 into 10 power minus 4 kilomole per meter square second. That's all. Okay. Straightforward problem. So you are basically option A is correct answer. Okay, first we'll read the question. So question is the following, that a gas mixture is in contact with a liquid. Component P in the gas mixture is highly soluble in the liquid. Okay, so that's the information we have to highlight. Component B is highly soluble in the liquid. Okay, so what that means to us? So that means if I have a equilibrium line y versus x, how do you expect this line to be? Imagine it's a straight line. Would it be having a high slope or low slope? Very small slope like this. Okay, so that's what this information means. So that means m, even though it's not given, it means it's actually very small. So what are they asking? Possible concentration profiles during the absorption of P are shown in the choices. Again, they are also talking about absorption. This is also an important information, because we know that for absorption, the inlet, the bulk concentration going to be above the line, and we are going to reach interface concentration somewhere here. If it had been a stripping, the bulk concentration should be below the line, and the interfacial concentration will be going upwards. So the direction is also important. So these are definitions. XY we know, XI, YI we know, equilibrium line also know. So question is, for this particular problem, what would be the right answer? Okay, so here absorption, right? Absorption means gas phase bulk concentration will be high, interfacial concentration will be low. Do we see that anywhere here? Maybe this one, right? You can see the bulk concentration is high, interfacial concentration is low. So this is looking like an absorption problem. Similarly, in the gas phase, it's going from interface to the bulk. So this is right. So this looks like absorption problem to me. On the other hand, if you look at this or this, the concentration of the bulk in the gas phase is increasing to the interface, towards interface. So that means the mass transfer must be happening in this way, liquid to solid. So obviously these are not correct. So it's between A and D. We know A is answer, but let's see why D is not answer. This information you can get it from this equilibrium line that they have given us a very soluble problem. Okay, so the y equal to x line would be somewhere here, right? Y equal to x is a 45-degree line where along the line y is equal to x, but we are having a line that is here. Okay, so here what will happen is, for a given x, y will be always smaller, right? That's what you see here. For the given equilibrium concentration of x, the equilibrium y will be smaller because m is very small. This case would have been the other way around, because y is larger than x, so you would m should be more than 1, but we know m is actually less than 1. Okay, so that's why obviously I think I like this problem because it allows, there are so many information available here about the type of absorption, whether it's absorption or stripping, and whether the equilibrium line is having a higher slope or lower slope. Okay, all that is nicely represented here. So okay, so this is a problem not in GATE because it can't be done in GATE. Okay, this is quite involved and a lot of, but I like this problem because it actually allows us to distinguish between the two approach of mass transfer rates that I was talking about, and you will actually get two different answers if you use the phenomenological approach versus the fundamental laws of mass transfer approach. But this is a concentrated system, so obviously we should use the fundamental laws of mass transfer approach, not the phenomenological approach. So it's quite a lengthy calculation, but anyway I will try, and then let's see what happens. So we have a wetted wall column, okay, and some diameter is given. Maybe this information may be useful for us somewhere. and this absorption of ammonia from ammonia air mixture with water. Okay, clear cut A diffusing in non-diffusing B, absorption problem. And what is given? YAG and XAL. What is XAL? Is 0.05. YAG is 0.8, quite concentrated. Okay, so as I said, anything above 0.1 mole fraction we are going to deal with this concentrated system. This is going to be a concentrated system. Okay, so we'll just write this. This is a concentrated mixtures. So if you want to draw some danger symbol, you can draw here like a skeleton or something. So this is a concentrated mixture, so you have to watch out for. And what else is known? Some new information which we never used before in previous problems, that is temperature. Okay, temperature is given 30 degrees, pressure is given 2 atmosphere. I don't know why these are given, but we'll see. And then the local liquid phase mass transfer coefficient measured at dilute condition. So KL is a mass transfer coefficient. It is actually obtained from some other measurements. Okay, not for this particular experiment, some other experiment which involves dilute conditions. Okay, so KL is 2.87 into 10 power minus 5 kilomole per meter square per second. And look at the units, it's actually meter per second, So what is the concentration units we should be using for this mass transfer? If the coefficient has a unit of meter per second, what is the driving force expressed in? This is a liquid phase, right? So then I'm using a wrong, so this should be Kc. So concentration should be given in molarities, mole per volume, mole per liter, mole per meter cube. Actually you can see it here. This is the units of the concentration, moles per meter cube. So in our terminology, we have Kc as a liquid phase mass transfer coefficient. Okay, so that is given, and then for the gas phase, the local Sherwood number for the gas is given. So Kg or Ky or Fg we don't know, but it is given in terms of Sherwood number, which is a non-dimensional number involving mass transfer coefficient. Okay, so Sherwood number is equal to 40. So you have to worry about how to define Sherwood number. And what else is known? Diffusivity is known. Okay, diffusion of ammonia in air is given, that is 2.297 10 power minus 5 meter square by second, and then of course equilibrium line. Compute local mass transfer flux, ignoring vaporization of water. So that we are talking about only A diffusing through non-diffusing B, water is not involved. It's only ammonia getting transferred from air to water. So we have mass transfer type of A diffusing in non-diffusing B. And we want to know what is Na. I'm not going to solve this problem, but I'll tell you what we can do. So we have to get Na. The way we should do this problem is already something we have discussed before. We know that local coefficients, even though they are not in mole fraction units, but you can convert them into mole fraction units based on the relationship I have discussed before. From Kc you can go to Kx if you want. From if you get from here, if you get from the Sherwood number, if you get something like Kc, you can get convert them into Ky. Okay, all the relationship we have given in the class. So essentially you will have access to the local coefficients in terms of mole fraction units. If you know that, you know the bulk concentrations also. So then you should be able to calculate the interfacial concentrations. And if you know the interfacial concentrations, then you can calculate the flux. So that's the roadmap, that's a plan. Now one of the challenges you might feel here is the mass transfer coefficients are not given in the right unit and you have to convert them. Okay, that's where you need the pressure and temperature, because you need to convert the units from concentration to pressure and so on. So, okay, that's where this temperature pressure will be used. And another complication in this problem is that this is a concentrated system, like I said before, and also it's A diffusing through non-diffusing B type. So you have to use this flux Na using F type coefficients. Something like this. Okay, so you need to get F type coefficient from the Sherwood number, whereas this interfacial concentration you should get from, again, the respective F type mass transfer coefficients. Okay, so this can be quite involved calculations, and you have to be careful about the units and other things. So you try this out, and we will probably post the solution in Moodle page maybe a little later for you to compare your solution. But I urge you to do it yourself based on whatever you've done so far. I've shown you all the methods of doing calculations of interfacial concentrations, calculation of overall mass transfer coefficients, calculation of fluxes. You should be able to use all these ideas and solve this problem. You have to only pay attention to this conversion of units for the mass transfer. That's the only catch. Okay, and then you have to use the expression for concentrated mixture, which we have done in one of the problems before. You have to use this kind of expressions. All right. Okay, so try this out. Okay, that's all. Stop, Nilas.